Hi everyone! So before I close Module 1, I want to congratulate all of you for diligently finishing this module. So I hope that you'll learn a lot from the very first topic up to the last topic of this module. So to give you a quick review of what we have learned, so take a look at the summary highlights of the lesson discussed. So we have learned in this module that the indefinite integral of a function is not unique as it includes the constant of integration denoted by capital C, which can be an arbitrary number. That is, the integral of f of x dx is equal to the function denoted by big F of x plus the constant C. Another lesson that we learned from this module is proper identification of u and du must be performed first before applying the integration of exponential functions formulas. Like number 1, the integral of e to the u du equals e to the u plus the constant c. Second, the integral of a to the u du is a to the u over the natural log of a plus the constant c, provided that a is greater than 0 and a is not equal to 1. Okay, we also learned that the knowledge of u substitution and understanding the process of evaluating integrals involving trigonometric functions are essential keys in evaluating integrals involving trigonometric functions. And in this discussion, we'll learn the following trigonometric formulas. Another is, if the integrand is a product of sine and cosine, then transform the integrand using the appropriate product formula identities as shown below. We also learned in this module that most integrals of products of powers of sine and cosine, tangent and secant, and cotangent and cosecant involve rewriting the expressions in the following forms. So for products of powers of sine and cosine, we can write this as the integral of sine to the nth x cosine squared x dx, or the integral of sine squared x cosine to the mth x dx. For powers of tangent and secant, so we can rewrite this as the integral of tangent to the nth x secant squared x dx, or the integral of secant to the nth x tangent x dx. For product of powers of cotangent and cosecant, we can write this as the integral of cotangent to the nth x cosine squared x dx, or the integral of cosecant to the nth x cotangent x dx. Also, in choosing your u and dv in the integrand, the laite can often help to take some of the guesswork out of our choices. So this acronym stands for logarithmic functions, inverse trigonometric functions, algebraic functions, trigonometric functions, and exponential functions. So the function that appears first in the list should be our first choice of u, and the rest of the integrand is dv. So those integrals involving repeated application of integration by parts, a tabular method is much easier to use. Like for example, if you're given, if your u is x squared plus x and your dv is sine x dv, so we have to differentiate the algebraic function until the derivative becomes 0. And then we take the integral of sine x to get negative cosine x. Then we take the integral again of cosine x to get negative sine x and cosine w. Okay, we also learn in this module that those integrals involving repeated applications of integration by parts, a tabular method is much easier to use. So let's say, for example, you're given the integral of the product of algebraic function and trigonometric function. So we have x squared plus x sine x dx. So from the laite acronyms, because algebraic is written first before the trigonometric function. So your u is x squared plus x, and sine x dx is your dv. And then we will differentiate the function a number of times now until the derivative of u becomes 0. So the first derivative of u, which is x squared plus x, is 2x plus 1. The second derivative is 2, and the third derivative is 0. Because u is differentiated thrice, so dv should be integrated 3 times. The first integral of sine x is negative cosine x. The second integral is negative sine x. And the third integral is negative of negative cosine x, which is positive cosine x. And then the integral of x squared plus x and sine x dx is equal to the product, is equal to the summation of the product of the diagonal terms. So this is alternate in sign, positive, negative, positive. So for the first product of diagonal terms, you multiply x squared plus x by negative cosine x. So we get negative x squared plus x cosine x. Next, because this is negative and negative is positive times positive, so the next term should be 2x plus 1 times sine x. Plus, for the last product, because this is positive, so 2 times positive times cosine x is 2 cosine x plus the constant c. So this is the final answer. Okay, we also learned that in algebraic substitution, we replace the variable of integration by a function of a new variable. So a change in the variable on integration often reduces an integrand to an easier integrable form. Okay, we also learned that if an integrand is a rational function in terms of sine x and cosine x, it can be reduced to a different rational function in terms of just the new variable z by the substitution z equals tangent 1/2 x. So the equivalent relations below are used to express the entire integral in terms of sine x equals 2z over 1 plus c squared, cosine x is 1 minus c squared over 1 plus c squared, dx is 2dz over 1 plus c squared. Then simplify and evaluate the resulting integral and then substitute back tangent 1/2 x for c. So this method of partial fractions examines a procedure for decomposing a rational function into simpler rational functions to which you can apply the basic integration formulas. Okay, the following steps now may serve as guide on how to apply partial fraction decomposition. So letter A, make sure that the degree of the numerator is less than the degree of the denominator. So if not, then you have to perform the long division. And then letter B, factor the denominator into the product of linear and irreducible quadratic factors. When you say irreducible quadratic, it is a quadratic that has no real zeros. Letter C, after the appropriate decomposition is determined, solve for the constants, and then rewrite the integral in its decomposed form and evaluate it based on the applicable integration techniques or integration formulas. Okay, so that's all for module 1. So in the next module, now we will discuss the application of integration. So the following are the sources and references used in this discussion.